The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Alright, so I'm going to work through problem number 13 for Physics 2020, Exam 2, year 2006. This problem says, approximately what magnitude of force, F sub m, must the upper arm exert on the lower arm to hold a 7.3 kilogram shot put? See figure arm. And basically figure arm is on this supplemental sheet that's given with the exam, right here. And it says, assume the lower arm has a mass of 2.8 kilograms and assume its center of gravity or center of mass is 12 centimeters from the pivot point. Okay, so I've basically redrawn the figure here, figure arm here. And so basically what we have is we have the lower arm, and this lower arm has mass of 2.8 kilograms, and we have an upper arm, and this upper arm exerting a force on the lower arm because we have a 7.3 kilogram ball that is being held up here by the hand from the upper arms exerting the force on the lower arm. And so basically what we have is a sort of system here where the ball is being held by the arm. And if I've basically created our coordinate system here where we have the y and the going up positive direction, and this is the positive x direction. Alright, so given this information, we're supposed to determine the force Fm. Okay, and excuse me. Basically, we have a force. So let's kind of like dissect this figure out to see what's going on. So we have some force. We have some pivot point. Okay, the pivot point is here on the arm, and we've got some forces that are acting. Okay, to cause this system to rotate. Okay, it's not rotating because the ball is being held up, but it wants to rotate. So we have some forces that are acting on this pivot point. Okay, so we have one force which we call Fm, and that force is acting at a distance of 2.5 centimeters from the pivot point. So that's actually 2.5 centimeters. So this is the pivot point. Okay. Then we have basics, and so this force is basically trying to is trying to cause a torque. Is trying to rotate this arm this way. Okay, because this is your pivot point. If you have a force acting down, perpendicular to the x direction, then it's going to try to tend to try to rotate this part of the section around the pivot point. So we have another force that's acting down, and that's basically the upper arm. Okay, we have the upper arm that's acting down. I'm sorry, the lower arm. Okay, and so we can call that force as F sub L, and we know that distance. It's acting. It's using. The force is acting at the center of gravity, which is 12 centimeters away from the pivot point. All right, and we have one last force that's acting, and that is the force of the ball, which is causing the system to rotate clockwise, and also the lower arm is going to tend to rotate it clockwise, and the upper arm force is going to tend to rotate it counterclockwise. And basically, this is acting at a distance of 30 centimeters away from the pivot point. Okay? So basically, here's our system in rotational motion. And we know that the ball is being held up, okay? So the ball is not falling down at all. So we know there's a balance. We know that the torques are balanced. And we can basically say that the sum of the forces, the sum of the forces is equal to MA, and that would be in translational motion. And if it's translational motion, we know that if it's balanced, that acceleration is 0, so that this whole term, right-hand side of the equation, becomes 0. But we're talking about rotational motion, so instead of the force, we're talking about torque. So we know that the sum of the torques, or tau, is equal to 0, which is equal to the sum of the R times the forces. Okay? Perpendicular forces. Okay. So basically, if we just, so we have, this is called the force of the ball. So we have 3 forces. So we have the force M acting at a distance, okay, at a distance of, let's convert that to meters. So 2.5 centimeters, and we know that there is 100 centimeters in 1 meter, so 0.025 meters. And so we know that we have the lower arm force that's acting at a distance. So this is, let's call that D1, and that's acting at a distance of 12 centimeters, which is equal to 0.12 meters. We'll call that D2. And then we have the force of the ball. That's acting at a distance of 30 centimeters, which is equal to 0.3 meters. And we'll call that D3. All right? And so we know that basically R in this particular case is our distance, our distances. So distance away from pivot point. And we know that the forces that are acting perpendicular to the axis, so this is basically acting perpendicular to this axis, is causing our system to rotate one way or the other. So if we can just sum these up, we know that it's equal to 0, and we should be able to solve for F sub m. So basically, if we say that we can use our coordinate system where, you know, if we're rotating this way, it's going to be, let's say, negative, and if it's rotating that way, it's going to be positive. Okay, so this is positive, and that's negative. But essentially, we know that Fm is going to equal to F sub L plus F sub B, because the torques are it's going to balance out. So that means the sum of these forces are going to equal to Fm. Okay. So, and that's actually incorrect. It's Fm times D1, it's the torques that are going to equal to each other. So it's FL times D2 plus FB times D3. Okay, the torques are going to equal to each other because we're talking about rotational motion. So, let's see if we can create some space here. So we know that Fm times the distance d1, but the d1 is 0.025 meters. That's going to equal to the force of the lower arm, okay, which is which is 2.8 kilograms times 9.8 meters per second squared, because we're looking for a force, times its distance, which is 0.12 meters, okay, and that's going to be plus the force of the ball, which is 7.3 kilograms times 9.8 meters per second squared, times the distance that it's acting, which is 0.3 meters. Okay? So we can solve this equation for Fm simply by just dividing through by the distance 1, which is equal to 2.8 kilograms times 9.8 meters per second squared times 0.12 meters plus 7.3 kilograms times 9.8 meters per second squared times 0.3 meters divided by this distance, which is 0.025 meters. And then when we plug that in for our calculators, we get 990 newtons. Okay, so basically all we did here was we used the same theory for as we did in translational motion. Basically, instead of summing the forces, we're going to sum the torques. And we know that if we're rotating counterclockwise, that has to balance out with all the torques that are rotating clockwise. So we were able to set up our system here, and in order to solve for the missing force, which was Fm. And we got an answer of 990 newtons.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.